This is gives me the greatest pleasure to introduce a sequence of two talks by one of our seminar organizers, Igor. I guess needs no introduction, and the title is here. So we please welcome Igor with the talk.
So first of all, I'm asked to pardon me my appearance because I have a back problem, so I'll be half sitting, and depending on how it goes, probably the second talk, we'll see if it's okay, or probably the second talk will need to find some volunteer to substitute me. Okay, so I would like to talk about work in progress. Part of it was already published. It's joint work with N.Nekrasov. And there is one time objective of this project. I'll talk only about some parts of it which is related right now to mathematics. Namely, I will talk about conformal harmonic maps of two torus in two spheres. And this is a subject of interest both for mathematics and for physics. For physics, it's called nonlinear sigma models. And in general, so let me start with simply definition of harmonic maps of a Riemann surface into a Riemannian manifold M. There are critical points of the action functional points of the action, and the action is just the integral over the surface h z bar g ij of x dz. I'll simply write d xi d bar x j dz dz bar. So x is a map. Xi are coordinates, some local coordinates on the Riemannian manifold. The metric or z and z is a complex coordinate on sigma corresponding to the conformal class of a metric on sigma. So h is a conformal factor here. And g is a Riemannian metric on M. So just that is by definition the critical points. And their interest, as I said, and actually, I don't know how many papers are written about sigma model. It's certainly hundreds in physics, and less, of course, but in terms of in mathematics. So in mathematics, harmonic maps of particular interest, conformal harmonic maps describe minimal immersions of sigma into M. So you're looking on minimal immersion, minimizing the area of a surface, and conformal means that in addition to condition that the equation, the map is harmonic, the condition is that if you take x, push back the metric on from M to sigma, this is in the same conformal class as H dz dz bar. So only these maps, these harmonic maps, describe minimal immersions of surfaces into Riemannian manifold. This condition is equivalent to the following constraint, that corresponding components of an classical analog of energy tensor momentum, namely their x the scalar product of dx equals to t z bar d bar x. So this scalar product has to be equal to 0. This is the condition that the metric, the pullback of a metric on M, is in the same conformal class as the original metric on this surface. This constraint, often called string constraints, and the classical analog of Virasoro constraint in quantum mechanics, when you put the condition that Virasoro algebra generator annihilate ground state for n bigger than -1, and Ln here is 0 for n less than 1. So the average of any expectation value of any Virasoro generator, which are coefficient of the expansion of energy momentum term, is 0. So this is the condition, the classical analog. And it's very hard to satisfy harmonic maps supplemented to this additional constraint. Okay, so our interest is the case, the simplest case, simplest case, of course, would be CP1, but the next and much more harder case is the case of a torus with any conformal structure on it. So sigma would be just z bar, subject to the constraint that z bar equals z plus omega alpha z bar plus omega alpha bar, with alpha being 1, 2, and omega 1 is 1, and omega 2 is tau. So we're looking on the complex torus and want to find harmonic map of this torus into the spheres. This is again, it's n-1 dimensional sphere with induced metric on it. Metric induced by embedding of a sphere into the Euclidean space. So it's called ON model in physics. N field. And for us, it's just to describe, we'll be interested to describe minimal immersions of a torus into an n-dimensional sphere. So in this case, equations of motion in a very simple way. It is d bar minus u, which is a function, u d bar, which is a function, smooth function on the torus, x. So x is a vector with coordinates xi equals 0. And subject to the constraint x scalar product, which is in fact, from what I will say, there is not much difference what particular choice of quadratic form you choose. Of course, properties of solution depend, but in fact, what we'll discuss embeddings of torus into some quadratic. It can be a sphere, it can be a de Sitter or anti-de Sitter space. Let's not focus on this. So it's some scalar product with constant coefficients by linear form on Rn, which the quadratic is embedded. So this is, again, as I said, it's a classical problem. And the most influential paper in this direction in mathematics is about harmonic maps of torus into spheres in three-dimensional sphere, better to say. So was the paper by Hitchin in 90s, in early 90s, I don't remember. So exact solution of ON04 model were constructing solutions were I want to use some color. Constructed. We'll see that the meaning of the word constructed, he is not, and maybe exact as well, it's not very constructed. I'll tell what actually by Hitchin using zero curvature representation found by Palmeier, Mikhailov, Zakharov, zero curvature representation of SU2 principal chiral field. So principal chiral field is the sigma model with target M that is a Lie group with invariant metric on it with phi invariant. And actually, this zero curvature representation is the starting point in all these numerous works in studying of, it was central for sigma model. So the equation of motion for SU2, which is isomorphic to O4, SU2. That's why that can be used to construct solutions to O4 model. So the equation of motion can be represented as a zero curvature representation. U is lambda minus 1 dz bar minus plus v lambda minus plus 1 equals 0. This is equation that is equivalent to the equation with u, which is dz x x minus 1 dx, and v is dz, and v is x negative 1 d. So it's currents of our map x of, it's a local picture of sigma into some Lie group G. Okay, so I spent some time describing what Hitchin did, and actually just to show the difference between the conventional approach used in all previous works on sigma models with the approach we use with Nikita, that goes some time back to my earlier works. So the zero curvature, so this equation for you being in V some matrices as in the algebra of SU2, the compatibility condition of two linear problems, just lambda minus 1 psi z bar lambda equals 0 dz bar plus v lambda plus 1 psi z bar lambda equals 0. And since we are working on the torus, so psi is a horizontal sections of this flat connection with coefficients u and v, and also depending on lambda. So we can define monodromies of this equation. Psi z plus 1.
Igor, quick question.
Yes.
Lambda, is this some number we've seen before, or just appears in this equation?
We haven't seen this lambda. Lambda is just a so-called spectral parameter. So this equation should be satisfied for any complex value of lambda.
Okay.
That gives you equation. So in order this equation, it's a rational function. So in order to get this equation, you have two equations equating to zero residues at lambda plus 1 and lambda minus 1. That's all.
Mm-hmm.
And these two equations are exactly, one of them tells you that u and v are logarithmic derivatives of some function. And then the second one gives the equation of motion.
Okay.
So it's a pencil of connection, flat connection, depending on additional parameter lambda.
Okay. Super.
Okay.
Thanks.
So you take psi z bar plus 1 lambda is psi, because coefficients are periodic, it is z plus z bar lambda. Okay, let me write b alpha of lambda, and here let me just write psi. So shifting z into two periods, you get two monodromy matrices plus omega alpha z bar plus omega alpha bar lambda. We get a monodromy matrix. And since this B alpha, and for each B alpha, you can define consider the curve defined by its characteristic equation, B alpha determinant of mu alpha minus B alpha, it depends on lambda, equals 0. It's an equation. I would like to stress that B of alpha is a meromorphic function of lambda. It's not, it's not meromorphic. It's entire function of lambda outside lambda equals plus minus 1. That's why this curve is not algebraic curve. It's analytic curve. And as we'll see, in general, it's very singular. So we take two curves, analytic curve gamma alpha. They're defined by equation that's embedding into C2 with coordinates mu alpha and B lambda. So what Hitchin proved, and it was absolutely unexpected result, that the projection Hitchin proved prove that the projection gamma alpha onto C, which is just nothing but projection on lambda coordinates. And it's 2 to 1 because in Hitchin case, B is a matrix of 2 by 2. So it's two-sheeted curve of lambda plane, has only finite number of odd branch points. That are the same for alpha equals 1 and 2. So it's the same, and this finite number of branch points defines which define a hyperelliptic curve. Now it's because there is only finite number of branch points. Curve. So for any solution to the O4 model, you may assign a hyperelliptic curve of finite genus and a certain divisor on it. And this divisor corresponds to the following. By definition, for each point on this curve, which he called spectral curve, there is a one-dimensional space of solutions to the eigenvectors for these matrices B. And this line bundle corresponds to a certain divisor. Okay, that was his main algebraic result, because actually, and here that's the delicate point. There is a way to construct the inverse map from a hyperelliptic curve and divisor. You can construct the solution to the zero curvature equation and correspondingly the solution to the harmonic map. But unfortunately, starting from arbitrary curve, you get not x as a function on the torus. The solution would be quasi-periodic function of z and z bar. So equations, probably equations on gamma. So that single out periodic, double periodic solutions. And we are interested in particular, we want to solve the solution to construct harmonic map of a torus, not some of universal cover, are transcendental. You will see later their analog in our approach, and they are transcendental in the same, in the following sense. You have a high modular space of hyperelliptic curve, and the condition that single out spectral curve, hyperelliptic curve that give rise to the solution of the problem are formulated in terms of periods of certain integrals, second kind integrals. And there is no hope, to some extent, to solve them explicitly. So it becomes just a kind of, maybe it's the best possible answer, but of course it's not completely satisfactory.
Igor, can I question?
Sure.
This solutions
yes.
solutions that we consider, what did they look like? Are they isolated points, or there's some deformations to solutions? And
no, first of all, of course, there are deformations. You can shift z by a constant.
Yes, okay, well, modulo that.
Yes, they are isolated point for each z, for each genus. There would be genus of a spectral curve. you expect only a finite number of points.
Finite number.
It's
And those,
natural because they are critical points of some nice functionals. They cannot be degenerate. So there are some certain convexes. Yes, we'll expect to have
okay. Finitely many points defined by some transcendental equation. That
finitely
that's
many points for each
genus.
G.
Okay.
This
And and the degree.
you can since any solution to ON model corresponds to some hyperelliptic O4 model, corresponds to some hyperelliptic curve of finite genus. You can assign a number to any solution.
Okay. And then the divisor, the degree of the divisor, that's fixed in terms of the genus of the curve.
Yes, it's
okay.
Genus plus minus plus the rank is.
And if I have this harmonic
again,
harmonic
Andrei,
map, is it difficult?
Andrei, there are deformation, of course. You expect finite number of curves, but then the divisor gives you a family of solutions.
Okay. So looking at the solution, I know what's its genus by knowing how big the deformation space roughly.
Okay, maybe yes. The answer yes.
Okay. And is there some other way to, if I have a harmonic map, is there some other way to know what the genus is, or it's not so easy?
I don't know.
Okay. All right. Thanks, Igor.
Okay. So Hitchin looked also on for O3 with some particular embedding in O4, like I can describe it, this embedding. There exists embedding of O3 into O4 such that you will get solutions to O3 model. So harmonic maps, very simple, basic object. Harmonic maps from a two torus into two sphere. Hitchin stress that there are, there is no spectral. So everything degenerates. So mu, this mu, is just a constant. So the map from solutions of ON model into the spectral curves in this traditional approach, it's not an injection. So there are solutions given zero or non-existing spectral curve. I would like to, especially, there are no spectral curve. There is no spectral curve. Mu alpha lambda is just identically 1. That was his observation. At the same time, there are solutions pretty well known since early work of Polyakov, Ilarian, and solutions of sigma of elliptic curve into CP1 actually are given by explicit formula x1 plus I x2 equals 2w divided by 1 plus absolute value of w squared, and x3 is 1 minus absolute value w squared divided by 1 plus w squared. It's a conformal harmonic map of two torus of elliptic curve into S2, where W is just an elliptic function, theta of its usual Jacobi elliptic function Z minus AI theta Z minus BI, the product I from 1 to L, with the only constraint that sum of A alpha minus sum of B alpha is 0. So this is how you can explicitly write conformal harmonic maps. And L here is the degree, or in physics it was called instanton number, of a map of torus elliptic curve into onto two-dimensional sphere. So the solution exists, and there is no way to get them out of standard approach. Okay, that was what I wanted to say about traditional approach for the solution of ON sigma model. We'll see the same with the reflection of difficulties in our approach. So Fermi curve approach. Actually, it's approach where you don't use anything familiar in the world of integrable system. No Lax representation, no zero curvature representation. You just use the following idea. Okay, consider, I recall that equation of motion for ON model is a Schrödinger equation. And actually U here is nothing but when you vary the functional, this is Lagrange multiplier coming from the constraint x equals 1. So if you vary the function without this constraint, you put as usual Lagrange multiplier, you get the linear equation. So the idea is the following. Forget about this. Let's first look on the linear equation and let's study it. And only, so we want to parameterize, not solution, we want to first parameterize the function U, which is the potential, in terms of certain data, and only after that, when we describe U in terms of certain spectral data, we'll turn to the equation. By the way, is it possible of this equation to find those that satisfy the constraint? And there is effective answer. Actually, this idea, I got it many years ago from the work of Cherednik, who just noticed that you can solve nonlinear Schrödinger equation looking on the linear equation dt minus dx squared plus u psi equals 0. And then as soon as you make the connection, express the potential in terms of solution, so psi squared, it immediately turns into non-linear Schrödinger equation. It's somehow delinearization of a linear problem again. And there is very straightforward way to solve the second part, if you know well the first part, namely the spectral theory of linear operators. I want to recall some basic facts about spectral theory. Spectral theory of Schrödinger equation. Two-dimensional, 2D Schrödinger equation. But actually what I'm saying, it's applicable to any two-dimensional linear operator with periodic coefficients. Okay, you have U, and we define Bloch-Flaquet locus is a locus of inside C2. So W1 and W2 are coordinates in C2. And Bloch-Flaquet locus described is a locus for which the equation Z bar W1, W2, the Schrödinger equation has solutions that are eigenfunctions for the monodromy operators. Okay, namely, you have a periodic operator acting in some space. Of course, if you're looking for eigen or solution to this equation into the space of also periodic function, most likely you will not find such a solution, or there would be a discrete set of them. If I put E here instead of 0, that will be equation for eigenfunctions of the Schrödinger operator. The spectrum, or in the space of periodic function, is discrete, and it's well-known theory. Now, I don't want to have periodic solution. I want to have a solution which is under this shift in Z W1, W2 is multiplied by the corresponding that is called Bloch-Flaquet multiplier. So it's quasi-periodic Z bar W1, W2. Of course. So you don't expect that for any W1 and W2 you find such a solution. But it is natural to expect that there would be some analytic locus inside C2 for which such a solution exists. So gamma Bloch-Flaquet is defined formally by the following. You take operator H psi equals, so H some periodic operator. You can, because it's periodic, you can restrict it onto the space of sections of a line bundle over torus, with W1 and W2 being multiplicator along 2 cycles. After restricting, that becomes HW1. So the operator now depends on W1 and W2. And you are just looking when this equation, linear equation, has solution. HW1, W2, restrict H onto the space of sections with multipliers W1 and W2. Unfortunately, it's not so easy because this operator is infinite dimensional. And having determinant is a delicate question, not so obvious. Example, I'll give you an example when the Bloch-Flaquier set as an analytic set in C2 doesn't exist. Namely, take the operator dx plus dx squared plus u of xy. So xy are two coordinates on a torus. And for this h, there is no Bloch-Flaquier set. The corresponding determinant cannot be defined, doesn't exist. And this is one of the reasons why one of the two basic fundamental equations in mathematical physics, so-called KP1, is not integrable in full sense. Luckily, the existence of Bloch-Flaquier set, I proved it effective description of gamma for H, which is a Schrödinger operator, was obtained in, I believe it's 89. I need, for further use, I need some instructive example to describe how looks the spectral theory of, or how looks the Bloch-Flaquier set for Schrödinger operator. Example, instructive example. Take H to be very simple, almost free operator, D minus 1. So I take potential being just 1. In that case, Bloch solutions, very easy to write. It is EKZ plus 1 over K, Z 1 over K plus Z bar K inverse. This is the solution. You just plug in, you see. And the corresponding Bloch multipliers, W1, equals EK plus K inverse, and W2 is IK minus 1 over K. No, sorry. W2 is EIK minus 1 over K. This is the monodromies of this operator along 1, and for simplicity, I'll take tau to be just I, rectangular structure on the elliptic curve. Otherwise, I should write for omega 2 some tau bar. I want to escape. Okay, so now let's look into this formula. This W1 of K, W2 of K explicitly defines your map of C with coordinates K into C2. And that the image of this map is the Bloch-Flaquet set. It's highly singular curve. P Bloch-Flaquet for this example has infinite number of double points. That can be easily found from the equation. They are indexed by pairs of integers. So you write k plus 1 over k minus k plus k prime 1 over k prime equals 2 pi I n k minus 1 over k minus k prime minus 1 over k prime equals 2 pi n, 2 pi m. This is two equations for two unknowns, k and k prime, and they corresponded to self-intersection, the preimage of some point, because if k and k prime satisfies this relation, then w1 and w2 at k and k prime, w alpha, k equals to w alpha of k prime. This is exactly the condition that there is a double point, self-intersection point of the curve. But there are infinite number of them. Let me just, it's easy to solve. It looks like, oops. So there are infinite number of them, plus minus. It's m plus I over n plus minus radical 1 minus 1 over m squared plus n squared. That's all. So you see, you have a lattice to a certain extent, up to some correction, of points that go to infinity with one choice of a sign. No. M plus I n 1 minus. So there is a sequence of points going to infinity, and they look like, roughly as m plus I over n. And for different choice of a sign, you have a sequence of points. So the limiting points are 0, k equals 0, and infinity. So there are two sequences of points indexed by integers, by pairs of integers, that are pre-images of double points of the Bloch-Flaquet set. So the Bloch-Flaquet set is singular. C can be seen as a normalization of the singular curve. And this normalization is of finite genus, namely genus 0. You remember, when I describe results of teaching, I said that this finite genus finite genus hyperelliptic curve is a normalization of the curve or analytic curve defined by characteristic equation. So here is toy example, what is happening. There might despite singularity of Bloch-Flaquet set, its normalization might be of a finite genus. Okay. Now, what happens with the curve when you consider d bar minus u psi equals 0, when u is not a constant, but arbitrary function under perturbation. Double points. So I see looking on u as perturbation of the free operator with constant coefficient. For constant coefficient, we know how looks the Bloch-Flaquet set and how looks its normalization. Now, the claim is, if you consider u as a perturbation, double points are resolved. Namely, instead of having a double point, the Bloch-Flaquet set becomes smooth. You have a, instead of intersection, you have a thin handle, if you wish, connecting these 2 points. Size of resolution is controlled by the exact formula, controlled by Fourier coefficient. Fourier coefficient of, so u is periodic function. You take Fourier coefficient u and m of u. So exactly, if u has non-trivial Fourier coefficient, that is first order of perturbation theory, the curve becomes, this Bloch-Flaquet set becomes smooth, infinite genus analytic curve, which looks not so bad because there is a full control of its asymptotic behavior on the infinity. That's how looks the general curve. The curve Bloch-Flaquet set corresponded to the general potential. I'll define finite gap or algebraic geometrical potentials u are those for which the normalization, I'll call it Fermi curve of Bloch-Flaquet set, is of finite genus. Namely, for some potential, that might be the case that the double point remains the double point. It is not resolved by perturbation. It moves somehow, but it's still the finite, it is still a double point of the Bloch-Flaquet set. So you take the normalization. So all but a finite number of double points I described remain singular, and you just resolve them, and you get a finite genus algebraic curve, which is called Fermi curve. Theorem. Finite genus curve, finite gap potentials are dense in the space of double of all double periodic functions z bar. You can think about this statement as some nonlinear analog of the following well-known fact. Any periodic potential can be seen. So consider trigonometric polynomials in two variables. They are dense in the space of all periodic functions. You just cut off all Fourier coefficients with indices big enough. And you can approximate any periodic function by trigonometric polynomials. There is nonlinear analog of this in the spectral theory. Of course, for generic potential U, your Riemann surface of Bloch-Floquet would be smooth, so there is normalization is the same and has the infinite genus. But there are potentials that are finite gap, namely their Bloch-Floquet curve remains singular, and the normalization of the singular curve is of finite genus. It may be, and increasing the genus, you just can approximate any periodic function by finite gap potentials. Okay, so where we are. Any questions at this moment? Okay, let me just continue. So inverse examples of finite gap potentials were constructed first by Novikov and Veselov. So you start with any let gamma be a smooth genus G curve with involution sigma having two fixed points. So there are 2 points fixed by the involution, P1 and P2, sigma with involutions, just interchange 2 sheets, because you can think about this curve as a 2-sheeted cover over the factor curve. And these points, P1 and P2, are points, branching points of this curve. Take, so the genus with 2 points, fixed points of involution, the genus of the curve gamma is related to the genus of the factor curve by the relation. It's twice as big as the other. So let D be a genus, a divisor, effective divisor of degree G, such that the relation D plus D sigma is satisfied. It's canonical class plus P1 plus P2. In other words, D plus D0, D sigma is the zero divisor of a meromorphic differential with simple poles, at the fixed point P1 and P2. Actually, this equation single out in the Jacobian its odd part, which is called prime variety. So given a point, a curve, and the divisor D, which belongs to the prime variety, prime inside the Jacobian, one defines psi, one defines a function psi z bar, p is a point on the curve with the following property: psi is meromorphic. It's a usual definition of the Baker-Hieser function, is meromorphic on gamma minus marked point P1, P2 first, with divisor of poles, with D being its pole divisor. And when P point approaches to P1, it has the form EKZ 1 plus some psi s, some regular function CZ bar, K minus S. K is a local coordinate. K inverse is a local coordinate in the vicinity of P1. And psi has the form EKZ bar 1 plus some psi S 1 to ZZ bar K minus S, and P is in the neighborhood of P2. That condition uniquely defines psi, and then the claim is that DD bar minus U psi equals 0, with u being the second logarithmic derivative is d bar of log prime theta function of u z plus v z bar. This u w1 z plus w2 z bar plus z, and that is just the potential. I can write some formula for psi. I don't think I need it. This is more or less standard fact. But here you can, I just presented in order to stress what is the problem. Because if you start with arbitrary curve, you get the potential, which is quasi-periodic. Here, W1 and W2 are certain vectors. You are in the prime variety, which is an abelian variety. You have two directions, W1 and W2, and you move. The solution, the corresponding function, is only quasi-periodic. So you need the condition that coordinates of W1 and W2 are in the lattice defining the prime variety. And these W1 and W2 are periods of certain abelian differential with the pole of second order at points P1 and P2. So in general, it's very easy to construct quasi-periodic solution. And the problem of satisfying just periodicity constraint is very hard. This problem is well known in the theory of the famous NUM equation. Again, NUM equations are considered integrable. You can even write the solution in terms of, explicitly in terms of some algebraic curve. But then you require that certain period on this algebraic curve equals 2. There is no hope to solve. This is the best what you can do. It's a lot. You can derive some consequences from this description, but it is not what you would like to celebrate at the end of the day. Okay, now the question. So we leave, this is the problem, finding Fermi curve satisfying periodic constraint. It is analog in our approach to the problem I described before in the framework of approach used by all the people, by Hitchin or the other. Okay, there is, unfortunately, although we can produce a lot of solutions, but the same problem persists. Suppose we know how to solve the periodicity constraint. It's unsolvable, but suppose. So now comes the other question. How to single out curves, Fermi curves, such that there are n points on it, and slightly cheating, but for simplicity, pi endpoints P, I, such that P, the function psi, you see, for any point on the curve, the function psi is a solution to our equation. Now we want to find a condition such that we can find points that evaluation xi of z, z bar of psi of this unique function at this point satisfies the constraint xi x comma x equals 1. So are there, how we know that the solutions to the ON model are those periodic Schrödinger operators for which this is satisfied. So how, in terms of curves and so on, describe this solution? So
Igor, question.
Yes, sure.
So this is this spectral curve we just discussed, the ones for this for the Schrödinger equation.
Yes.
Is it obvious that it's the same as the one which we discussed in the Hitchin situation, or it's related to that?
Again, it's not obvious at all. Actually, it's completely different curve.
I see. Okay.
It's completely different. Interrelation between two approaches. In each of them, there is a spectral curve. It's completely open question. I can state that they are different because I will, at the end, of course, it's clear I will not finish my talk in the remaining 10 minutes, but I will, if you...
But we obviously hope that you will feel better next week and can continue next week.
Yes, that's why probably instead of talking about degenerations of real normalized differentials, I will continue this talk. I want to finish it. But again, Andrei, these two spectral curves are distinct for the following argument. For all three models, as I said, in the Hitchin approach, there is no spectral curve at all. It's trivial. And the spectral curve in our approach exists. And moreover, I can explicitly describe it as an irreducible algebraic curves whose irreducible components are spectral curves of the elliptic Calogero-Moser system.
Okay. For instance, they're not hyperelliptic at all, right?
No, they are not.
Okay.
They're not. Again, it's two at this moment disconnected approaches. The example with O3 model shows that ours is more productive than conventional one.
But I apologize. So this would be a very naive question. So in this zero curvature Hitchin world, there was like two matrices and then some spectral parameter lambda, which was just something else. And so So could it be that there is some, in fact, a surface of which these two curves are different sections of some surface, which in fact, well, here also you can have. For Schrödinger equation, you can also have energy, right? You can also make it a surface.
No, it's not an energy. Energy here, Andrei.
Yeah, I know. Here's set to zero. Set to zero, but
you have two Bloch multipliers.
Right, but in principle, you could consider it to be a surface. But it's not the case that those are two different curves that somehow, different slices of the same surface. Not the case.
It would be extremely interesting. Again, I have no idea of the theorem I'm going to state gives a hope that probably there is some relation. Maybe in general, these two curves, Hitchin in the conventional approach, in Hitchin world and ours, are the same. We don't see it. Let me just state.
Yeah, okay. I apologize. I don't want to take up your whole time, so please continue.
So this theorem, this is, it was Nekrasov. Irreducible spectral curve gives solutions to or n plus 2m twisted model. I'll explain what twisted means. If and only if on gamma, on this Fermi curve, there is a function lambda. I call it lambda because probably it's the same lambda as it was in Hitchin approach with m bigger than 1 simple poles. In a way, we defined the Fermi curve. It was an abstract curve. It was not embedded in anything. The claim is that it gives solutions, so you can find points satisfying equation of motion for O n plus 2m model. Let me explain what it is. If it's a cover of degree m over the surface, so we get the constraint of the curve, and this curve has a function and produces solution. So what it twisted means? So twisted means that x1 x n plus 2m represent x1 x1 x n. First n coordinates are periodic. X n plus j is Bloch function z plus omega alpha, z bar plus omega alpha bar is a j of x n plus j. So we allow which solutions not to be periodic, but also Bloch solutions, and x n plus m plus j would be with x a with multiplicators So sorry, it's alpha minus 1. So the relation, quadratic relation is x1 square plus xn square plus xn plus j times xn plus m plus j equals 1. So you're taking a sum for j. This is some modification of the problem. It makes easier to deal with curve. The reason is that actually having periodic potential U is a problem of one level. Then you need to find to satisfy the condition that this function psi is also periodic, but it's in general it's only quasi-periodic. It's another layer of difficulties. So what I was planning to complete today, I haven't come even to the beginning of saying about conformal maps. So what is the most recent result proved just maybe a week ago with Nikita. There is a certain symmetry of the Schrödinger equation called Novikov-Veselov hierarchy is a symmetry of ON model. So we found an infinite number of commuting flows acting on the solutions of ON model. From that, we will derive statement Fermi curve corresponding to curves responding to solutions of ON model for any n of ON model are of finite genus. Remember, one of the results of the key result of Hitchin, when he proved that the corresponding hyperelliptic curve is hyperelliptic, it has only a finite number of branch points. Now the claim is the solution we constructed with Nikita are all solutions. So we constructed solution starting from the curve of finite genus. Now they claim they are all. And that your arguments are so fundamental and simple. I can explain them. Do I have 2 minutes more, Andrei?
Sure. Yeah. Yeah, of course.
You see what is happening. You have some nonlinear equation. If you have symmetry, then the symmetry is a solution of the linearized equation. Linearized equation is an elliptic, in case of you're dealing on the torus, is an elliptic equation with certain coefficients. Elliptic operator has only finite dimensional kernel. So symmetries must be linear dependent because we have infinite number of them. They become linear dependent. That tells you that there are certain commuting operators, and then by standard argument, the correspondence curve is algebraic. So that's what was my plan for today. But actually, the end of this story, I was trying to convince you to a certain extent that there is no hope to get an explicit answer, because all answer you might get, it was obtained by Hitchin, it was obtained by us in terms of curves satisfying some transcendental equation. It turns out that all these difficulties do not exist for conformal harmonic maps. So it turns out that conformal harmonic maps, the corresponding spectral curves, can be explicitly described as a spectral curve of elliptic Calogero-Moser system. An instanton or spectral number is the number of particles in the corresponding Calogero-Moser system. What Calogero system has to common to do with ON model, I have no idea. But that would be the goal of the second part of my talk, just to explain the meaning of words of Novikov-Vesilov hierarchy. Then in 2 minutes after that, I will derive that the corresponding spectral curve must be finite genus. And then we'll turn to the discussion of what is in the title of my today's talk. Okay, any questions?
Yeah, questions, please. I'm just repeating the call for questions to start.
Okay.
Can I come back for the question to the very beginning? Suppose I have one of this harmonic maps. Then its deformations are solutions to a linear problem. It's just like you said a second ago.
Yeah.
And so this would be a finite dimensional space of deformations.
Yes.
But did I understand correctly that this deformation space, you can kind of globally say what it is? This deformation space is like some abelian variety, or some maybe, roughly an abelian variety.
It's abelian variety. You are correct. That is what I'm going to say, yes. And
so that's coming, right? That's coming next time?
That's coming, because the deformation is the curve is fixed, and deformation is just this extra parameter divisor. So it's going to be the abelian variety is going to be a pre-variety of the corresponding curve.
Okay.
And again, Andrei, this is the point, because the deformation space finite dimension. That is the reason why the genus of all spectral curves in the Hitchin approach and in ours, we are always sitting in finite algebraic situation. It's algebraic in the sense that spectral curves are not curves of infinite genus. They are algebraic curves. They are finite genus.
But now suppose
the problem is that they are cut out of model space of all curves by transcendental equations.
Right. But now suppose I have, instead of a round sphere, I have some Riemannian manifold. Then again, this deformation space finite dimensional again by the same argument. And what do you think this deformation space might look globally? Is it still going to be is that going to be something bad, or is it going to look again like an abelian variety, or some is that?
It's not clear. That first of all, there might be no deformations. Probably you see the
but the deformation is some kind of index thing, right? So if
it's not like that the dimension of its index, yes. But
Yeah, so
there
if
might
I
be-
have some index in a round sphere and then I perturb this sphere, the index is gonna stay the same. So it's uh
I have no idea. It's interesting, but I have no idea how to describe
okay.
the deformation space for not. Okay, we have results for sphere for all standard sigma mod like sphere, CPN
Uh-huh.
of the same nature. For CPN, it will be not the prime variety; it will be just the Jacobian variety of the spectral curve.
All right. That sounds great. More questions? Well, if there's no more question, then we'll be looking forward to next talk, and we all hope you feel well enough to give us the continuation. We wish you speediest recovery, and thanks again. So please, everybody, join me in clapping hands and wishing
you.
Igor the speediest recovery.